In this example, we're asked to find dy dx at the point 0, 2 for the parametric equations x equals e to the 2t minus 1, y equals e to the t plus 1 on the interval for t's between negative infinity and infinity. So the first step is just to know how to find dy dx for parametric equations. And the way we do that, so dy dx equals dy dt over dx dt. So then we need to actually compute dx dt and dy dt to continue. So let's start by doing that. So dx dt, that's just going to be the derivative of this x expression with respect to t. Okay, so if I do that, the derivative of e to the 2t is 2e to the 2t, and then minus 0, of course. And then dy dt is just going to give me e to the t if I take the derivative of this expression here, e to the t plus 1. All right, so then I can go ahead and fill in what dy dx should be. So dy dt, which was e to the t, over dx dt, which was 2e to the 2t. So if I wanted to, I could write this as e to the t over 2 times e to the t quantity squared. So we see that we have a factor of e to the t that can cancel out. So I end up with 1 over 2e to the t power, or 1/2 e to the negative t. And that is dy dx. So for any t value that I plug in here to dy dx, this would give me the slope of the tangent line on the xy graph of these parametric equations. But we're not quite done yet because I'm specifically asked to find dy dx at the point 0, 2. So 0, 2 is an xy point, right? 0 is my x value, 2 is my y value. But if I look here at dy dx, this is expressed in terms of t. So then, to find dy dx at the point 0, 2, I basically need to take this xy point and translate it into a t value so I can plug in to my derivative here. So this isn't going to be too hard. Basically, I can just solve 0 equals e to the 2t minus 1, right? So I'm just taking my x expression from up here and setting it equal to 0, right, since I'm interested in the point where x equals 0. And then I'm going to solve for the corresponding t value. So here I'm going to get 1 equals e to the 2t. I can take the natural log of both sides, and I'm going to get natural log of 1 equals natural log of e to the 2t. Now the natural log of 1 is just 0, so this gives me 0 equals 2t, which tells me that t equals 0. But just to make sure that we did things correctly, just to verify, let's also check this y coordinate as well. Right, so in other words, I'm going to take my y equation here, e to the t plus 1, and set it equal to 2, right, since my y coordinate here is 2, and I'm just going to make sure that I get the same t value. Okay, so this gives me e to the t equals 1. If I take the natural log of both sides, I get t equals the natural log of 1, so t equals 0. Okay, so good. So then t equals 0 corresponds to the point 0, 2. So then what I want to do is I want to evaluate dy dx at the point t equals 0. So that's going to give me 1/2 e to the negative 0, which of course is just 1/2 e to the 0. E to the 0 is 1. So I just get 1/2 as my final answer. So 1/2 then is the derivative or the slope of the tangent line for these parametric curves at the point 0, 2. In this example, I'm told for the parametric curve x equals 3 cosine 2t, y equals 4 sine of 2t for t's between 0 and pi, determine all points where there is a horizontal or vertical tangent line. So to begin this example, I'm actually going to show you a picture of what the graph of this parametric curve looks like. So these parametric equations actually trace out an ellipse, right, which you can see in this picture. And an ellipse is an oval-like shape, so I have radii of different lengths here. Now, you could have also figured this out by eliminating the parameter in much the same way that you would do for a circle. So for example, I could write these equations as x over 3 equals cosine of 2t, and y over 4 equals sine of 2t. And then if I realized that cosine squared of 2t plus sine squared of 2t equals 1, which is just a Pythagorean identity, then I could write that also as x over 3 quantity squared plus y over 4 quantity squared equals 1, which is the equation of an ellipse. But anyway, this is an ellipse. So if you recall what we were asked to do, we were asked to find all points on the curve where we have either a horizontal or vertical tangent line. And I just wanted to show you a picture first so you could get a sense of what we're looking for. So if I just glance at my curve here, I can see several spots, 2 specifically, where I would have a horizontal tangent line, right? I would expect to have one here at the top and at the bottom of my ellipse, and then it looks like I should have a vertical tangent line here on the right and on the left. So this is what we sort of expect, but let's try to do the work algebraically and see if we can get to the same point. So since we're dealing with tangent lines, that suggests that I'm going to need to find the derivative. And I want to find specifically the derivative of y with respect to x, dy dx. That's going to give me information about the tangent lines on the xy graph that we just looked at. So if you recall, for a parametric equation, dy dx equals dy dt over dx dt. So I need to compute both of those derivatives to start out. So let's start out with dx dt. So x is given by 3 cosine of 2t. So if I take that derivative with respect to t, I'm going to have my constant of 3 out front, and then the derivative of cosine is negative sine. I'm going to have a factor of 2 out front, though, from the chain rule. So negative 2 sine of 2t. So in the end, negative 6 sine of 2t is my derivative, dx dt. And then dy dt, I have a constant of 4 out front, and then the derivative of sine of 2t is going to give me 2 cosine of 2t. So in the end, 8 cosine of 2t. So then my overall derivative, dy dx, is going to be dy dt, which was 8 cosine of 2t, over dx dt, which was negative 6 sine of 2t. Or I could reduce and write that as negative 4 cosine of 2t over 3 sine of 2t. Now we could even write this as negative 4/3 cotangent of 2t, but I actually think this form here is going to be a little more helpful for us in what we want to do next. Okay, so now that we have the derivative, we can start thinking about where the horizontal and vertical tangent lines might occur. So let's start by thinking about the horizontal tangent lines. Now a horizontal line is going to have a slope of 0, which means that I want to look for the points where dy dx, which is the slope of the tangent line, equals 0. Now, what I have here is a fraction, right? Negative 4 cosine of 2t over 3 sine of 2t. So in general, a fraction is going to equal 0 at the places where the numerator equals 0. As long as those places don't also make the denominator 0, right? I don't want to get 0 over 0 here. I just want to get a 0 on the top. So let's think about then the places where negative 4 cosine of 2t would equal 0. And remember that specifically I am interested in the interval between 0 and pi. So I don't need to worry about this negative 4. I can divide that out so that I just end up with the equation cosine of 2t equals 0. So to solve this expression, what we want to do is we want to think about the places where cosine equals 0. So I know first of all that cosine equals 0 at pi over 2. So then if 2t were to equal pi over 2, then this equation would be satisfied, right? Cosine of pi over 2 equals 0. Or 3 pi over 2 would also give me a cosine value of 0. And then so on. 5 pi over 2, 7 pi over 2, and so on. So let's solve these little equations for t. So 2t equals pi over 2. I'm going to get t equals pi over 4. Okay. And then here I'm going to get t equals 3 pi over 4. For t equals 5 pi over 2, I'm going to get t equals 5 pi over 4 if I solve that expression. So at this point, though, I can see that I'm already outside of my interval here. T is between 0 and pi, so I don't need to continue. And I'm really just going to pick these two t values here. T equals pi over 4 and t equals 3 pi over 4. So that tells us the t values at which there's a horizontal tangent line, but what we're actually interested in is the points themselves where there's a horizontal tangent line. So we just need to find the associated xy points here. So if I wanted to, I could just set up a little chart. So x is given by, if I scroll back up here, 3 cosine of 2t, and y is given by 4 sine of 2t. Okay, and I have t values of pi over 4 and 3 pi over 4 that I'm interested in. And I guess one thing we should do very quickly just to make sure that we haven't made a mistake here is just make sure these t values don't give us a 0 on the denominator of our fraction, right? Because we said we didn't want 0 over 0. But if I just glance at this, so if I plug in pi over 4 here, I'm going to get 3 sine of pi over 2, which is non-zero. And if I plug in 3 pi over 4, I'm going to get 3 sine of 3 pi over 2, which once again is non-zero. So we're good. These t values are only going to give us a 0 in the numerator. Okay, but anyway, so if I plug in these t values to x and y here, for pi over 4, that's going to give me 3 cosine of pi over 2. Now cosine of pi over 2 is 0, so this should just give us 0. And for my y value, I'm going to get 4 sine of pi over 2, which is 4 times 1, so 4. And then if I plug in 3 pi over 4, for x I'm going to get 3 cosine of 3 pi over 2, which once again is going to give me 0. And then for sine of 3 pi over 2, which should give me -4. So it looks then like my actual points where I have a horizontal tangent line are 0, 4, and 0, -4. And if I look back at my graph really quick, that makes sense, right? We said our horizontal tangent lines, we expected to be at the top and the bottom of the ellipse here, and those do actually occur at the points 0, 4, and 0, -4. So that part it looks like we did correctly. So now let's work on finding the vertical tangent lines. And this is going to go much the same way. We need to realize, though, that the slope of a vertical line is undefined. So what we actually want to get here from dy dx is a 0 in the denominator. So something of the form a non-zero number over 0. Once again, I don't want to get 0 over 0 here. I just want to get a 0 in the denominator. So if you recall, dy dx was -4 cosine of 2t over 3 sine of 2t. I want to end up with a 0 just in the denominator to get an undefined slope. So I'm going to be solving 3 sine of 2t equals 0, or equivalently, sine of 2t equals 0. So we can go about this in the same way we did when we were solving our cosine equation. I want to think about the values, or I want to think about the places where sine is 0. And specifically, I want to be thinking about t values between 0 and pi. So I know, first of all, that sine of 0 equals 0. So 2t equaling 0 would be an option. And then the next value would be pi. Sine of pi equals 0. So we could have 2t equals pi. We could have 2t equals 2 pi, right? Sine of 2 pi is 0. And so on. 2 pi, or 2t equals 3 pi, and so on. So if we solve these guys, this first one is going to give me t equals 0, and then t equals pi over 2, and then t equals pi, and then t equals 3 pi over 2, but at that point I am out of my interval here. So it looks like I just want to stick with t equals 0, t equals pi over 2, and t equals pi. So those are the t values for which I'm going to get a vertical tangent line. But once, okay, so let's also just make sure that those don't give us a 0 in our numerator. But cosine, so I'm just going to think about plugging in these t values to cosine of 2t, right? So cosine of 0 is non-zero, that's good. Cosine of pi is non-zero, so I'm good. And then cosine of 2 pi is non-zero, so I'm good there as well. Okay, good. So these values are only going to give me a 0 in my denominator. Okay, so let's set up a little chart then to find the associated x, y values here. Okay, so we'll start with a t value of 0. If I plug that into my x equation, I get 3 cosine of 0, which is 3 times 1, or 3. And for y, I get y equals 4 sine of 0, which is 0. Okay, so that point is 3, 0. If I plug in pi over 2, I get x equals 3 cosine of pi, which is 3 times -1, or -3. And then I get y equals 4 sine of pi, which is 0. So that's the point -3, 0. And then if I plug in pi, I get x equals 3 cosine of 2 pi. That's 3 times 1, which is 3. And I get y equals 4 sine of 2 pi, which is 0. So once again, I get the point 3, 0. Okay, so then the points where I have a vertical tangent line are 3, 0, and -3, 0. And let's check that out with our picture, see if we got that right. Okay, so here's our vertical tangent lines on these right and left ends of the ellipse, and 3, 0 and negative 3, 0 look correct. Okay, so this is how you go about finding horizontal or vertical tangent lines for parametric curves. Or you could also be asked something like, find the point where the slope of the tangent line is 1/2, or something like that. And you would go about that in exactly the same way.